Hello everyone, welcome back to the alcohols reaction chapter. In this video we're going to be looking at diols. So we've only been seeing one alcohol, but I want to now go through diols. So if you don't know how to name diols, I just want to quickly go over that. So if I have this one here, I'm just going to make this right here. If you were to have this molecule, how would you name it? And I'll just draw in that hydrogen for clarity right there. Again, this is just to help you understand how to name diols. So we know that if we want to name just a normal alcohol, that's a terrible line structure. Okay. This would be 1-propanol, propanol, kind of like that. But if we have a diol, it turns out we would name this. So this is, the carbon chain is 1, 2, 3, 4. So that's butane. And we have 2 alcohol groups in position where we want to make these the least as possible. So we're going to go from the right to the left. So we're going to name this one as 1 and then this one as 3. So we have, let me write the name here, 1, 3, butane diol. Alrighty, and that's how we name diols. So let's get into our first set of reactions here. We have a little bit of review from, if you're following the David Klein's book, chapter 8, alkenes. We remember there's 2 reactions that will give us what's called dihydroxylation. And you can get 2 different outcomes of stereoselectivity depending on the reagents you use. So if we use a peroxy acid, let me draw the carbon first, CO3H, right? And then we follow it with some acid. We know that it's going to follow through a little intermediate here, right? It either being on the top or the bottom of that ring. Sorry, my wedges look like shit, but it is what it is. So we have that, and then that it gets protonated here through the acid, and then that water comes in as a nucleophile, right? Because it gains some electron density from giving up that proton, and it's going to attack through backside attack. So actually, to make it look a little nicer, it will come through the backside, and we get an anti-conformation. So our final product will look like this here. So let me draw that. We'll get an OH on the wedge, right, made from those initial 2 steps. And then we have water. Why am I drawing that? Oh, fuck it. We'll draw it that way. We'll have, it will come in as water. It will become deprotonated to give us OH. So that is anti, right? That's an anti-way to make a diol from 1 carbon away from each other. That's important here. We're going to see in a second how we can prepare alcohols where they're further than 1 carbon. This is restricted, really. So this is a very rare case. Sometimes you need a diol very close to each other, like if you're doing bupropion, hydrochloric acid synthesis. That would be an example of when you might want to use that. Okay, so if we want to add sin, right? Not sin going to hell, but sin as in having your chiral centers, adding that OH on the same side. So instead of here where 1's a dash, meaning it's pointing down or away from you if you're observing the molecule, or this one, it's pointing in front of you or up, you could say, that's anti. Sin just means we're going to add like this, right? So like this. Do you remember the reagents by chance? That would be a miracle if you did, but right, we're going to add either wedge, wedge, or a dash, dash, right? So hopefully you remember. It is a little, I hope you never looked at the mechanism, but it's osmium tetroxide, right? That's what you start with. You have water in there too, and you have this molecule called NMO. I have it written out over there, NMO, all right? And if we just I'm going to very simplify this mechanism because I Honestly, I hate this mechanism. It's so annoying. Oh my goodness. But I'll just kind of give you the notes here. So we don't make a ring. We make the osmium tetroxide is gonna bond as such, and then osmium. And don't worry about the other bonds; they're not important. So here's our osmium. I'll just draw it as a little green blob. That's osmium, right? So it attaches with 2 of its oxygens, and then water comes in and basically yeets off the osmium into this osmium complex, basically. And then NMO is going to, osmium is going to attack and steal that oxygen. It's going to be regenerated, and it will come back to do the same thing to our alkene. So given that the fact that osmium tetroxide bonds in one way or another, it disallows for that stereo selectivity to occur. So now let's get into some reactions in this chapter and how we can prepare diols. Okay, so if you want to make a diol given more space, in the reactions we saw with alkenes, it was 1 carbon away from each other. So to be honest, that's not very synthetically useful compared to what we could do. Let's say you do a synthesis and you make a product, and you want to put a diol on a hydrocarbon here. So 1, 2, 3, 4, 5, 6, 7, 8. So octane, right? You want octane. You want to add 2 diol groups in this position and this position here. So you couldn't just use an alkene. That would be a little too annoying. I mean, I'm sure you could figure something out, but it's not very, your yield would probably not be good given all the steps, right? Because transfer error, just error in the lab. So we can do a different reaction. We'll see, I believe it's chapter 19, aldehydes and ketone reactions, how we could add an aldehyde or ketone. So let's just say you take octane, you do a bunch of synthetic steps, and you get this here, and we said we wanted it, I believe, here, right? So you want to make a ketone, a diketone, and you want to install those keto groups in the positions where you want your diols, right? So there's synthetic strategies to do that, and I'm sure it wouldn't be too difficult. But our next step here is to do a reaction that we just saw. If you remember the reagents, in this case we'll use lithium aluminum hydride, and then we need to follow this up with an acid workup step, so 2, and we're going to just go generically H3O+. Okie dokie. So we know that lithium, will go through step 1 here to start. Step 1 will give us this here with oxygen with a negative charge and oxygen with a negative charge. 2 equivalents of acid come in, and they protonate those to give us our diol. So you can kind of see how we're using the reaction. That's kind of why I like to cover it, and that's why the textbook covers it that way. So you have another way to prepare diols through reduction by lithium aluminum hydride or another delivery agent, sodium borohydride. So that was our alcohol diol reactions, how we can prepare them. Next, we're going to look at something called the Grignard reagents, and that would be pretty interesting to look at. So hope you guys enjoyed, and I'll see you in the next one. Goodbye.